Thank you, John. Thank you, everybody. The title of the presentation today, Design and Progress of FloWave, the tank we're building. I'll canter through in 7 minutes a little bit of the design of what we're making and also then some of the progress of build and see where we are to date. And then a little bit about what the future holds as well. And through that, I'll also touch on why we're doing it and why it's so important. So I'll just crack on if that's all right. So the full name of the facility is the UK All Waters Combined Current and Wave Test Facility. The FloWave tank for short, this is much easier. We are a commercial subsidiary of the University of Edinburgh. We're funded by the university and also by the Engineering and Physical Sciences Research Council to the tune of about £10 million to build this facility as a national facility for the benefit of all. And if I quote the EPSRC, a national facility of international importance. The most important thing about the tank is that it's compared to most other test facilities, it's circular, fully enclosed with 168 wave makers, which allows us to create multi-directional sea states. And also unique in this tank is that we can also add in current to that as well. We can flow water. We have 2.5 million litres of water in the tank, 2,500 tonnes. We can flow that at just under 2 knots. And the whole principle there is that we should be able to simulate anywhere on the UK continental shelf for both wave and current, and both at the same time. So big waves off the west coast of Scotland, fast flows in and around the Orkney, the Skerries, the Isle of Wight, and everywhere else. And the important thing is with the scale of this. It's 25 metres across. That means that we can test single devices, we can test multiple generations of devices, but most importantly, we can also test arrays of devices. And obviously the main principle here is that we can use this for de-risking technologies and optimizing the technologies, but also projects as well as the technologies. So just to run through very quickly what we have, we've a very large building. It's a little bit like the size of a small IKEA. At the right-hand end on this graphic, we have workshops for fixing stuff when it breaks, making stuff, and kind of tweaking things on the fly. But a lot of that's because our twin remits effectively for doing academic research, but also commercial work. With that as well, the control center and project engineers that help get everybody through this process of being in the tank. If I zoom in on the tank itself, this is a sectional cut through. You can see one half of the 168 wave makers, and perhaps most importantly, in the lower part of the tank, below this floor, which in this graphic is in its operational position. This is a buoyant floor that floats to the top. You jump off the gantry and you can work on the floor, fixing your devices to it. You lower the floor down, and then in the lower part of the floor, we have 28 what we call flow drive units. If you imagine 7 on the right-hand side are sucking the water out of the tank and putting it into the chamber in the middle of the bottom. 7 on the opposite side are sucking it out and putting it back into the top of the tank and create a current, effectively a conveyor belt of current through the tank. By stepping up and stepping down opposite pairs, we can step that current direction around the model. And obviously, because we are moving the water past the model, we have fully developed shear flows. We can add in turbulence. The turbulence in the tank is very low. It's lower than the ocean. So you can actually check arrays, wake effects, blockage effects, and so on. But also you can add in designer turbulence, designer shear, as you like. So it's a really sophisticated wave and tidal test facility. But most importantly, I guess the best thing to summarize it is it's a sea simulator. It is a real sea simulator. So looking in plan view, this gives you an idea of 3 generic tidal turbines in the middle of the tank here, with the flows across the tank from the 7 to the opposite 7. We can make hot spots, we can make twin spots, we can make a more smooth spread of current across the whole the whole tank. On the left, we have a tidal chart. It's effectively an nice ellipse that's very idealized. On the right is a real one from Orkney, and you can see there, you probably can't see actually, each of the bullet point or the points on that chart is 1 hour difference around high water. And you can see it switches in this location from 3 knots in one direction to nearly 4 knots in the opposite direction in under an hour. So that's where the difficulties come in deployments, and that's another use of the tank, is practicing those deployments in these very challenging energetic sites. So we've applications for wave and tidal. We've other applications for offshore wind. We can use the tank like a towing tank for towing, for example, the gravity bases or floating wind. And we can also look at vessels on dynamic positioning when they're doing installations. We have other marine operations type roles as well, in particular those people that are developing sort of tidal, specialist tidal device installation vessels. And we have a number of sort of other subsea type applications for inspection, ROVs and AUVs, and other instrumentation that you might want to deploy on the bottom. This is a great place to practice that kind of work. So benefits for all of that, depending on what you're doing with this sea simulator, is you can refine the performance before you actually spend too much money cutting steel, and you can reduce the risk as much as reasonably practical before you go offshore and incur those high costs. Also for the money men, if you're looking at your energy yield predictions from arrays, then you can validate in a real physical modeling the computation and numerical modeling that you've already carried out. And I guess also for OEMs and device developers and project developers, they can actually compare devices side by side because of the excellent repeatability that we have in the tank. I haven't mentioned on this slide, it's survivability. If you want a 100-year storm, there's no waiting for 100 years, we just turn it on. So going into construction progress, this is what we started with on the King's Buildings campus in Edinburgh. Very ugly building, riddled with asbestos. This is a very fast canter through all the pictures now. So we get rid of that. We develop a clear site. This is a little bit over a year ago. We shape out the size of the tank. I'm hoping that the JCB in the middle here will give you some idea of scale. The white dots you can see are all the piles for the building, which then we pop on top. So the structure starts to go up. This is our crane coming in, 5-ton crane. Everything in the building is designed around the 5-ton model. So when I say big scale, I mean big scale. A bit difficult to get it in. We had to leave some of the roof beams out before we could lower the crane beam into its carriage. We then dug out a massive hole, 35 meters across, 6 meters deep. Luckily, we didn't find any rocks, but then we filled it with our own rocks, which is about 100 tons of steel and 400 tons of concrete. If I can just get this to, let's do slide. The movie won't play. Can I go back a slide and play that pour? Thank you. Here we are. This is an 18-hour pour in 16 seconds. Oh, it's a bit slow. Okay, so that's our 500-ton slab going in. Then we, outside, while we're going on with that, we're changing this basically very kind of building site structure into something that looks a little bit slicker. At the same time, we're doing validation testing on some of the gear we're putting in. This on the right-hand side is one of the FloWave units being tested, mounted vertically. We're getting on, this is a control room. It's a little bit James Bond lair looking down into the tank. It's a fantastic view. Down inside, the concrete walls are going up, it's all circular. We get a chance to play and get in there and see what we've got. It's very impressive when you're there. I can only show you some of the photographs, but if you're there and get it in 3D with your real eyes, then it's really very impressive. The view from the control room is really the best point. So we're getting then into the scientific equipment that goes into the tank. These are the FloWave units going in. We have done a series of visitors. This is Neil, who's going to speak a little bit later. We have a collaboration with EMEC so that we can actually, the first site that we simulate, the real actual site will be 1 or 2 of the EMEC berths. So you can come to us and replicate an EMEC in the tank. It's a press of a button. And then once Neil's away, we crack on, put in a few more wave makers, and we get a lot closer to completion. This is the other end of the hall looking back towards the control room, which you can see up the top there. And then this is the latest picture I took on Monday before I came up here. All the wave makers in place, and we're starting to put in the turning vanes, as we call them. So we're just, the next steps are to complete the flow drives and complete the floor. We're going to fill the tank in August and then flush out the junk that's all in there that comes with all the massive surface area of equipment. We commission and calibrate, and we have some shakedown clients coming in, and then we're moving into commercial operations. So now's the time to engage with us if you're interested in being part of that process and testing at the tank. So that's me. Thank you.